Hi everyone, my name is Harvard Nguyen, and today I will be talking about the formation of an enamine from a ketone. I'm sorry, I forgot to draw out the product that we're supposed to get in the end with our question. I'm so sorry about that. Let me fix that really fast. Oh, shoot. Yes, got it. Okay. All right, so let's read our question together. Under acidic conditions, show the mechanism of the ketone reacting with a secondary amine to form an enamine. Explain how reaction equilibrium applies to certain steps in the mechanism. So first, what I'm going to do is I'm actually going to work out the mechanism. It's not too long, but I think it's best if I work out the whole mechanism in one one explanation, so you guys get the general feel of the pattern. And then I talk about reaction equilibrium afterwards, and see how it relates to our following question. All right, so when it comes to any mechanism, there are usually four mechanistic steps that we should know: nucleophilic attack, loss of leaving group. Sometimes you'll encounter rearrangements, and another one would be proton transfer. So in this mechanism itself, we will see a nucleophilic attack with our dimethylamine, and that we'll see a lot of proton transfer, a lot of protonation and deprotonation, and then we'll see a loss of a leaving group eventually formed through those proton transfer steps. So let's get started with our mechanism. So the first step would be to do a nucleophilic attack, basically of this diethylamine onto this ketone, and this ketone is heptathione. All right, so let's get to it. So we're gonna have this. All right, basically, I'm gonna react it with, sorry, the diethylamine. All right, so boom, and we're gonna get rid of that. We can get rid of that double bond. That's that carbon double bond to the oxygen, and we're gonna create something like this. Yeah, there we go. Mm, and then we can get this and each. All right, so we're gonna get a structure like that. And remember about stereochemistry. Why do I have stereochemistry here? It's because this carbon is bonded to four different groups. Remember, the longer carbon chain it is, the more priority it has. So this one is going to be bold and this one will be dashed. All right, now we're going to do a proton transfer. Basically, we're going to protonate this oxygen right here to get rid of that you see that negative charge right there? We're going to try to get rid of that. So we're going to do a protonation step. All right, so do a protonation step. Here. All right. So, get that. This should have a plus charge. All right. Now, next, what we're gonna do is we're actually gonna deprotonate this time. We're gonna get rid of the proton in here. This is gonna be really essential towards forming our enamine. So we're gonna do a deprotonation step to get rid of the proton on the amine. Our new structure will look like this. Mhm. Get something like that. Okay. Now that we have that, next what we're gonna do is we're doing another proton transfer step. This time we're gonna try and add a proton onto the O to form H2O. Now, the thing to know about H2O is that it's a good leaving group. So eventually, what do you think it'll do? It will eventually leave, which is actually perfect towards forming this enamine. So we're gonna do a protonate. We're gonna protonate the OH to form H2O. All right, so that's the next step. And the mechanism so far, not too bad, just nucleophilic attack, and basically so far has been all proton transfers. Uh, and so yeah. All right. All right. So then basically with this H2O, what we're gonna do now is we're gonna break off, we're gonna take off the leaving group, and then we're gonna bring, you see this pair of electrons on the end? We're gonna bring it here to form that double bond, so we're gonna form a carbon double bond to nitrogen as well. So we're gonna bring this down here, and then we're gonna kick off the H2O, I'm so sorry, the water, because H2O is a good leaving group. So next. And next, when you form the double bond, you don't gotta worry about stereochem anymore because carbon is only bonded to three groups again. So you're gonna have one, two things somewhere, I think. Yes. All right. And then afterwards, what you're gonna do is you're gonna do a protonation. Sorry, a deprotonation step. Sorry. So with one of these carbons, there's a little proton that could be hanging right there. Basically, what we're gonna do is we're gonna deprotonate to form the enamine, which is our final step. So let me use that, and then sorry, let me. Okay, and then voila, we get our final product that we wanted, which was which is the enamine that we are looking for, exactly like it. All right. Now, the second part of our question asks how a reaction equilibrium applies to certain steps in the mechanism. So basically, reaction equilibrium refers to whether if a reaction could be reversible or irreversible. And there are some general rules that applies to every mechanism step that we have talked about when working through mechanisms. And some of the ones I've covered actually today. So I want to go over some of those general rules right now. So when it comes to nucleophilic attack, how you know if a reaction is reversible or irreversible is based on uh, when the nucleophile attacks if it can create a good leaving group. So let's say, for example, we had a structure like this, and then we had bromine attack. Well, bromine's a good leaving group. So basically, that's why it is reversible. Now, let's say, for example, we had something such as a hydrogen, and hydrogen will react to break off this ketone, break up this ketone. Oh, I'm so sorry. Now, hydrogen, it's already stable. It wants to stay there, so it's not a good leaving group. So therefore, this reaction is not. This reaction is irreversible. All right. Next would be let's talk about carbocation rearrangement. So with carbocation rearrangement, how it works basically in terms of reaction equilibrium, basically a lot of the time it's more often irreversible because the more stable the carbocation is, uh, the more it dominates the equilibrium. So basically, here we have a structure that was secondary, but then you do this hydride shift. Now it becomes tertiary, and tertiary is stronger than secondary. Therefore, this reaction will go forward, and because the tertiary dominates in this rearrangement. Now, for loss of leaving group, it's basically fairly simple, similar to nucleophilic attack. Basically, if we have a good leaving group, that means it can also function as a good nucleophile. Therefore, the reaction would actually would be reversible. For proton transfers, um, basically, for the most part, proton transfers are reversible. However, there are some extreme cases, such as if you're working with such a strong base. So with let's say for example, like this water is getting deprotonated with a really strong base. So basically, when you form the conjugate acid, the pKa is way greater than the original acid, and therefore this makes the reaction very irreversible. Another way we could look at reaction equilibrium is when looking at the pKa values. So that's why it's sometimes good to have a little bit knowledge of pKa. Basically, reaction equilibrium will be more favored towards the weaker acid, basically the higher pKa. So in this reaction, the pKa is 18, while it's 15.7. So the reaction arrow, as I drew it, is, oh, I'm so sorry. I meant to actually draw this one a little shorter. So let me get rid of that and just draw like a little short one right there. So it's supposed to be like a little bit shorter. So basically it's gonna be more favoring towards this side because the pK is higher and it has the weaker acid. So let's look back at our mechanism and see where some of these general rules apply. Now, there will sometimes be some exceptions, but those are just the general rules when looking at some of the mechanistic patterns. So basically for the proton transfers, like I said, for the most part, most of them are reversible, except in extreme cases. Let me see. We do see that with a loss of a leaving group. This one's a good leaving group, therefore it is reversible. Um, we did have a nucleophilic attack here. However, we weren't like planning to try and break off this diethylamine. Therefore, it is still reversible. It was only if when we attack the nucleophile that it forms like uh, the nucleophile becomes like a good leaving group. However, we weren't ever planning to make this diethylamine leave as we wanted to form an enamine. Therefore, the reaction equilibrium is still reversible during this mechanism. Therefore, those are just some of the ways how reaction equilibrium does apply to some of the steps in this mechanism. Thank you so much, everyone, for listening. I hope this lesson gave a better understanding of how enamine formation works. Thank you so much, everyone.